Welcome back to Talk Tensors. I'm excited for today's deep dive. We're going to be looking at this paper on a new system called Linear MoE.
Sounds very interesting.
It is. So basically, it's all about combining linear sequence modeling. This is like, a more efficient way to handle those really long streams of data that these models work with the whole mixture of experts thing.
Right, MoE.
Yeah, exactly. And it looks like this could be a pretty big deal in terms of, building AIs that are even more powerful and can handle even more. So let's get right into it.
Absolutely. I think, one of the things that's always been a challenge with these large language models, these cutting edge AI systems we see powering things like advanced chatbots and really complex language tasks, is how to make them both more powerful and more efficient at the same time. And it seems like this paper is really trying to address that head on.
For sure. And they're basically trying to combine two really promising areas of research, right? So you've got linear sequence modeling, which, offers a way to process those long sequences of data much faster. So the time it takes kind of scales nicely with how long the input is. Right. And then you've got the MoE approach,
right,
where only certain parts of the model, those specialist experts, are activated for specific inputs. So you're not wasting all that computation on parts of the model that aren't even being used.
Yeah, it's all about being selective and efficient. And that's really the heart of what Linear MoE is trying to achieve. They're bringing together the speed and efficiency of linear sequence modeling, especially for these long sequences, with the targeted activation and resource-saving aspects of MoE.
Okay, so it's like getting the best of both worlds in terms of speed and efficiency. But how does this Linear MoE system actually work? They mentioned two main components in the paper, right?
Right. So they've got this modeling subsystem, which is really cool because it can actually work with different types of linear sequence modeling. So, you're not limited to just one specific approach to LSM. And then they've got the training subsystem, which has been specially designed for speed and efficiency, especially when you're working with these super long sequences of data, which, let's face it, is pretty much the norm in this field now.
So this training subsystem, they've really put a lot of thought into how to make it work well with all this new, more efficient processing of longer sequences.
Oh, yeah. And one of the most interesting things they did was they didn't just stop with a pure linear MoE system. They also explored these, what they call hybrid models, which kind of blend these linear MoE layers with the standard transformer MoE layers.
Interesting. So they're mixing and matching a bit, seeing if they can get even better results by combining these different approaches.
Exactly. It's like they're asking, okay, we've got this new super efficient way of doing things, but can we strategically combine it with the strengths of what we already know works well in these transformer models? And you know what? Their initial results are pretty darn promising. They're showing some real efficiency gains, and the performance is right up there with the best of them across a whole bunch of different tests.
Well, that's exciting to hear. I'm really interested to see where all this leads. But before we get too far ahead of ourselves, let's step back a bit and look at the history, the research that's led us to this point. How did we get to this Linear MoE system?
Well, the paper starts by painting a pretty clear picture of just how widespread these mixture of experts architectures have become in the top tier AI models we see today. They list a whole bunch of them. I mean, there's Gemini 1.5, which is huge. There's even reports of it being used in GPT-4. And then there's Mixtral, DeepSeek V2, Qwen 2, and a ton of others. And all of these rely on this idea of having these specialized expert networks, these little sub-brains, if you will, inside the larger model. But there's a catch.
There's always a catch, right?
Right. So while a lot of the MoE research out there has been super focused on, figuring out the best way to route information to those experts or how to make the expert layers themselves even better, one fundamental part of these models has stayed pretty much the same. That's the attention mechanism.
The attention mechanism, yeah, that's the part that really determines how the model focuses on different pieces of information, right?
Exactly. And, most of the time they're still using this Softamax self-attention that comes from the original transformer architecture. And that, as we've talked about before, can become a real bottleneck when you're dealing with longer and longer sequences of data. Sure, softmax attention is powerful, but the more data you feed it, the more computationally expensive it gets. Like the cost goes up quadratically with the length of the input.
So it's like you try to process a large document or a huge code base or even just a really long conversation, and the whole thing starts to slow to a crawl because this attention mechanism just can't keep up.
Yeah, exactly. And this becomes a massive problem when you're trying to train these models efficiently for tasks that need to handle long chunks of text. So in parallel to all the advancements we've seen with MoE, there's been this growing wave of interest in something called linear sequence modeling, or LSM.
And LSM is all about making sure the computational cost scales linearly, not quadratically, with the length of the input. So instead of things getting exponentially more difficult as the input gets longer, they just increase at a nice steady pace.
Exactly. And it's actually kind of cool how they do this. They draw inspiration from those older recurrent neural networks, but with a twist. Instead of just using single numbers or scalars to keep track of the internal state of the model, they use matrices, which are like, whole grids of numbers.
Right. I remember from my linear algebra days, matrices can represent much more complex relationships between different pieces of information.
Exactly. And this allows these LSM methods to be way faster when you're training them. And here's the kicker. It also means they don't need to store this massive KV cache during inference.
Ah, the KV cache. That's basically where the model keeps a record of everything it's already seen in the input, so it can use that information to predict what comes next.
Right, precisely. And for these standard transformer models, the KV cache gets bigger and bigger as you process longer and longer sequences, which just gobbles up memory. It's like trying to cram all your books into a tiny backpack. Eventually, it just won't fit.
And that becomes a huge limitation, especially when you're trying to run these models on devices with limited resources, or when you're working with these massive data sets.
Totally. But LSM sidesteps that whole issue by using a different way to compute its output. Instead of relying on this constantly growing KV cache, it keeps track of the special memory state that gets updated step by step as it processes the input.
Okay, so it's like, instead of keeping a record of every single book you've ever read, you just keep track of the key takeaways and insights that you can apply to whatever you're reading next.
That's a great analogy. And the result is that you get this constant memory footprint no matter how long your input is. And the paper actually shows how you can describe this whole process mathematically as a recurrent neural network, where this memory state evolves as you feed in new information.
So it's taking inspiration from RNNs, but doing it in a way that avoids some of their traditional limitations.
Oh, right. And here's what's really fascinating. They point out that other approaches to LSM, like those state space models and linear RNNs, have actually shown a lot of similarities in how they handle these memory updates. So even though these different methods might seem pretty distinct on the surface, underneath there's a shared computational structure.
Right, like different branches of science all relying on the same fundamental laws of physics.
Exactly. And the paper actually presents this elegant, unified mathematical framework that describes how these memory states are updated in all these different LSM methods. It's like having this universal language for understanding and implementing these various approaches. And if you check out table 1 in the paper, they actually list out a whole bunch of different LSM methods, like various types of linear attention, SSMs like the popular Mamba architecture, and linear RNNs like RWKV. And they show how each of their specific update rules can be expressed within this single unified framework.
So it's like they've created this incredibly flexible toolkit where you can swap in different LSM components while still working within the same overall framework.
Yeah, exactly. And this flexibility is one of the things that makes this linear MoE system so powerful.
Okay, so now we've got a good understanding of this unified LSM framework. How does this all fit into the larger MoE picture in Linear MoE?
So in a nutshell, the way they build a linear MoE architecture is by taking these linear MoE blocks and stacking them up one after another like building blocks.
And what's in one of these blocks?
Each block has two main parts. First, you have the LSM layer. And remember, this can be any one of those linear attention, SSM, or linear RNN methods we just discussed. They've got multiple options for each. And then you have a standard MoE layer.
Right, the MoE layer is where the model gets to choose which of its expert networks to use.
Exactly. And to make sure everything trains nicely and doesn't go haywire, they also add in these normalization layers before each of the LSM and MoE layers.
So it's like the LSM layer is taking care of processing the sequences in this really efficient way. And then the MoE layer is adding in this extra dimension of expertise, allowing the model to really specialize its computations.
Right on. And when they build a model entirely out of these linear MoE blocks, they call it a pure linear MoE model. And these pure models have some really nice properties.
I thought they're pretty efficient, right?
Oh, absolutely. Because they're using LSM for all the sequence processing, they're both super efficient for training and for inference, which is, when you're actually using the model to make predictions. But like with anything in life, there's a bit of a trade-off.
Oh, there's always a trade-off. What's the downside here?
Well, What they found was that these purely linear MoE models, while really good in a lot of cases, they don't always perform as well on tasks that really rely on remembering specific information from really long chunks of text.
Okay, so it's like they might be great at processing the information quickly, but they might not be the best at remembering every little detail from, say, pages and pages ago.
Yeah, you got it.
Mhm.
And this is especially important for things like in-context learning, where the model is supposed to learn from examples you give it right there in the input,
Yeah.
or for tasks where the model has to, reason over really long documents and remember specific facts. So to address this, they came up with these really clever hybrid linear MoE architectures.
Hybrid architecture. So it's like a blend of the new and the old, a mix of the efficient and the more memory focused.
Exactly. It's all about finding the right balance. And what they do is they combine these efficient linear MoE layers with those standard transformer MoE layers that we're more familiar with. The idea is to get the efficiency of the LSM approach, but also keep the potential for better memory recall that you get with those standard attention mechanisms.
So how do they go about building these hybrid models? Is it just a random mix of layers?
Not quite. They have a system for it. They basically replace some of the linear MoE layers with standard MoE transformer layers at specific intervals in the model architecture. Like they give these examples in the paper where they use a notation like, say, LLL to represent a purely linear MoE model, and then something like LNLN to represent a hybrid model where L means a linear MoE layer and N means a standard transformer layer.
So you can control how many of each type of layer you have and how they're arranged in the model.
Exactly. And the ratio of those standard layers, it can be tweaked depending on the specific task you're trying to do and how important memory recall is for that task. It's all about finding the sweet spot, that perfect balance between efficiency and performance.
Okay, so let's dive a bit deeper into the training subsystem, because it sounds like this is where they've really made some breakthroughs, especially when it comes to efficiently training these models on really long sequences.
Oh yeah, the training subsystem is a big deal. And one of the key things they focused on was adapting and extending a parallel training technique called sequence parallelism, or SP, specifically for linear MoE.
So sequence parallelism, as I understand it, is all about splitting up those long sequences of data and processing them in parallel on multiple GPUs.
Right. It's like having a team of chefs working together on a giant banquet. Everyone focuses on a specific part of the meal, but it all comes together seamlessly in the end. And for linear MoE, they really had to get creative with how they implemented SP to make it work efficiently with these new LSM modules.
They're building on previous work in this area, right? They mentioned something called LASP and LASP2.
Absolutely. They're taking those ideas and really running with them. LASP was pretty clever. It used this ring-based communication method where the different GPUs would pass around these intermediate memory states. The whole point was to keep the amount of data that needed to be transferred between GPUs as small as possible. Then LASP2 came along and simplified things a bit by using a more direct, all-gather communication strategy.
So they're constantly refining these techniques to squeeze out every last bit of efficiency.
Oh, totally. And with linear MoE, they've taken these SP techniques and expanded them to handle the entire system. So now you can efficiently train all those different LSM modules in parallel, which is crucial when you're trying to scale up training to handle these massive sequences of data on huge clusters of GPUs.
So this sequence parallelism, it's a real game changer when it comes to training these large language models, especially when you're working with these super long sequences. It really allows you to break down that computational workload and distribute it across multiple GPUs in a way that just wasn't possible before.
Right. It's not just about speed either. It's also about making sure that you're using your hardware resources as efficiently as possible, especially with all those memory states flying around.
Speaking of different types of layers, what about those hybrid models we talked about earlier? The ones that combine the linear MoE layers with those standard transformer MoEs. It seems like implementing sequence parallelism for those hybrid models would be even more complex.
You're absolutely right. It gets a lot trickier when you've got these different types of layers all mixed together, each with its own quirks and computational needs. So the researchers had to come up with a new approach, a more integrated way to handle SP that would work well across both linear MoE and standard transformer layers. And they did.
I'm impressed. So how did they do it?
Okay, so for the linear MoE modules, they use a single all-gather or reduce-scatter operation to synchronize that crucial memory state across all the GPUs. And the cool thing is that the amount of communication overhead this involved. It only scales up with the number of GPUs you're using, not with how long your input sequence is. So even if you're working with a really long sequence, the communication overhead stays manageable.
That's really clever. So no matter how long your sequence gets, the communication burden doesn't explode.
Exactly. And then for those standard attention modules, they use a different approach. It's an all-gather-based strategy that's similar to how they train those really large language models like Llama 3. What they do is they perform an all-gather on those key, K, and value V-tensors across all the GPUs, and then each GPU does its own local computations on its chunk of the query Q tensor.
So they're strategically splitting up the work and then bringing it back together in a way that minimizes those communication bottlenecks.
Right. And there's a good reason why they chose this all-gather approach for the standard attention layers. See, those K and V tensors, they're often much smaller than the Q tensor, especially when you're using techniques like grouped query attention, which is pretty common. So the overhead of doing an all-gather on those smaller tensors, it becomes less of a problem compared to the time each GPU needs to spend doing its local computations.
So it's all about choosing the right tools for the job.
Absolutely. And on top of all this, they also talk about something called hybrid parallelism, which adds even more flexibility to the whole system.
Okay, hybrid parallelism. So this is where things start to get really interesting.
Right. So with sequence parallelism in Linear MoE, you've got a lot of freedom in choosing how much you want to parallelize things. You can set the sequence parallel size to be any factor of the total number of GPUs you have. This means you can easily combine SP with that classic data parallelism, where you're basically splitting up your training data across both the batches of data and the different parts of each sequence. And the great thing is that their system works perfectly with the standard data parallelism techniques and that sharded data parallelism, which helps you manage all those model parameters during training without things getting out of hand. But it doesn't stop there.
Of course not. There's always more.
Right. They also support tensor parallelism, TP, pipeline parallelism, PP, and expert parallelism, EP. TP is great because it works really well with all the matrix multiplications you do in LSM, while PP and EP are more about working at the level of those individual linear MoE blocks or those MoE layers, just like how they're used in those regular transformer models.
So many ways to parallelize. It's like they've given you every tool imaginable to scale up your training process.
Absolutely. You can mix and match all these different parallelism strategies to get the most out of your hardware, especially when you're training those really big linear MoE models on those giant distributed computing systems.
It's amazing how much thought they've put into optimizing this whole training process. Now, one thing that always comes up when you're training these large models is how to deal with different sequence lengths in a batch of data. Some sequences are longer, some are shorter, and it can be a real pain to handle efficiently.
Yeah, that's a classic problem. The typical solution is to do what's called padding, where you basically add a bunch of dummy data to the shorter sequences to make them all the same length as the longest one.
But that seems so wasteful. You're doing all these computations on data that doesn't even mean anything.
It is. And while there are some clever tricks you can use with standard transformers to get around this, Linear MoE actually has a pretty simple and elegant solution. They process the entire batch of sequences as one long, continuous sequence.
Okay, so it's like they're ignoring the fact that there were ever separate sequences in the first place.
Exactly. And by doing this, they can handle all those different lengths without needing to do any explicit padding. So it's much more efficient, especially when you have a lot of variation in sequence lengths within a batch.
That's really clever.
Oh.
So we've talked a lot about the theory and the high-level ideas behind Linear MoE, but I'm really curious about how all this is actually implemented in practice. What tools and libraries did they use to bring all this to life?
So they built the entire Linear MoE system on top of this really powerful platform called Megatron Core. It's a super well-established and highly optimized open source library based on PyTorch.
Ah, PyTorch, the go-to framework for deep learning.
Exactly. And Megatron Core is specifically designed for training these massive neural networks on GPUs. It provides a lot of those foundational building blocks you need, like all the infrastructure for distributed training and all sorts of optimizations.
So it takes care of all that low-level stuff so the researchers can focus on the really innovative aspects of their system.
Exactly. And remember those two main subsystems we talked about earlier, modeling and training? Well, the Linear MoE system is structured around those. But here's the key thing. They designed Linear MoE so that it doesn't require a lot of modifications to Megatron Core itself. It basically sits on top of Megatron Core as this independent layer.
So it's like they've built this powerful extension without messing with the core of the system.
Exactly. And that's a really smart design choice because it means that users can easily benefit from all the latest advancements in Megatron Core without worrying about compatibility issues with Linear MoE. It's like having a modular upgrade that seamlessly plugs into your existing system.
That makes a lot of sense from a practical perspective. So let's talk about the modeling subsystem a bit more. What does it actually provide to researchers who want to use Linear MoE?
So the modeling subsystem, it's like a treasure trove of all the building blocks you need to create and train your own custom Linear MoE models. It's super modular and everything is designed to be reusable, which is awesome.
So you're not stuck with just a few predefined models. You can really experiment and build something that's tailored to your specific needs.
Right. And they've included everything you could possibly need. For starters, they have implementations of all those main LSM methods, linear attention, state space models, and linear RNNs with multiple options for each. It's like a buffet of LSM goodness.
So give me some examples. What specific implementations did they include?
Well, for linear attention, they've got things like BLA, lightning attention, retention. For SSMs, they've got Mamba 2, and for linear RNNs, they've got HDRN2 and RWKV6. And the cool thing is that they're constantly adding new methods as they come out.
So it's a constantly evolving toolkit.
Totally. But it's not just the LSM modules. They also have the standard MoE layers, those combined linear MoE blocks, various normalization techniques, embedding layers, you name it. They've even got a library of pre-configured linear MoE models that are based on some of the really popular open source MoE models, like Qwen2, DeepSeek V2, and Mixtral.
So if you want to get started quickly, you can just grab one of those pre-configured models and go from there.
Exactly. And all they've done is they've taken those existing models and replaced the standard attention layers with these more efficient LSM-based layers while keeping the rest of the architecture the same. It's like giving those models a performance upgrade.
I like the sound of that. And of course, they also provide all those essential tools like tokenizers, model converters, usage examples, and all sorts of helpful utilities. It really seems like they've thought of everything.
Oh, yeah. They've gone all out. And then there's the training subsystem, which, as you know, takes advantage of all those awesome parallel training capabilities that Megatron Core provides.
So you get all the benefits of Megatron Core's parallel training, but with these specific optimizations designed for Linear MoE.
Exactly. You get all those advanced parallelism techniques, tensor, sequence, pipeline, context, and expert parallelism, all working seamlessly together. But as they pointed out, those original implementations of tensor parallelism and sequence parallelism in Megatron Core, they weren't real designed with LSM in mind. And they didn't fully support SP for those hybrid models. So they actually went ahead and created their own optimized approaches for TP and SP that work perfectly with both LSM and those hybrid architectures.
So they really went the extra mile to make sure everything was perfectly tuned for Linear MoE.
They did. And on top of that, they also inherited all those other great features from Megatron Core, like mixed precision training, activation recomputation, distributed optimizer, distributed checkpointing, CPU offload. I mean, the list goes on and on. They've even added support for FP8 precision on those fancy new NVIDIA Hopper GPUs using NVIDIA's Transformer engine.
Wow, they're really squeezing out every last drop of performance.
They are. And to make those MoE layers even faster, they've integrated mega blocks, which is this cool technique that uses block sparse operations, and the grouped GMM library, which has these super optimized PyTorch kernels for MoE computations.
So it's like they've taken this already high performance system and supercharged it for Linear MoE. Okay, let's talk about evaluation. How do they actually measure how well these Linear MoE models perform?
So first off, they built in this offline text generation capability right into the Linear MoE system itself. So you can easily generate text and then evaluate it. But here's the really cool part. They also made sure that their system plays nicely with all those other popular evaluation frameworks out there, like OpenCompass and LM Evaluation Harness.
So you're not locked into using their own evaluation tools. You've got options.
Exactly. And remember that bidirectional weight conversion capability they built between Hugging Face Transformers and Megatron Core.
Yeah, the one that lets you easily move models back and forth between those two frameworks.
Well, that turns out to be a huge advantage for evaluation, too, because it means they can take advantage of all those great pre-trained models available on Hugging Face and use them for training in their system. And then they can evaluate the models they train in Megatron Core using all the different evaluation pipelines available in Hugging Face Transformers.
So it's like they've connected their system to this whole ecosystem of tools and resources, which makes it super easy for other researchers to adopt and build on their work. Really smart move. Okay, let's get to the good stuff, the actual results. What did they find?
All right, so they ran a bunch of experiments using two main series of linear MoE models. They had a smaller series called A0.3B2B, which had a total of 2 billion parameters, but only 0.3 billion of those were active at any given time. And then they had a larger series called A1B7B. And within each of these series, they trained up different versions of the models, each using a different LSM module.
So they really wanted to test out how well those different LSM methods performed in the Linear MoE framework.
They did. They tested BLA, retention, GLA, DeltaNet, Mamba 2, HGRN2, and RWKV6, all implemented using the Triton language. And then they compared all these linear MoE models against a baseline model that used the standard attention mechanism, which they implemented in Megatron Core. Oh, and they also compared them against models using that super optimized Flash Attention 2 implementation.
So they're really trying to see how Linear MoE stacks up against the best of the best.
Exactly. And for the base MoE architecture, they used the Qwen2 MoE model. They trained all the models from scratch on a huge chunk of data, the first two parts of the Slim Pajama dataset, which comes out to roughly 100 billion tokens. And they were very detailed in the paper about their training configuration, so other researchers can easily replicate their results.
Transparency is always good.
Yeah.
So what did they find in terms of training efficiency? Was Linear MoE actually faster?
Oh yeah, definitely. They focused on measuring the training throughput, which basically tells you how many tokens the model can process per unit of time, and the memory usage on those 8 A100 GPUs. They kept the total number of tokens processed per iteration constant at 16,000, and then they played around with different sequence lengths from 2K tokens up to 16K tokens and different batch sizes. And what they found was really interesting.
I'm all ears.
So that baseline model, the one with the standard attention mechanism, it showed the classic pattern. As those sequences got longer, the memory usage went up quadratically, and the throughput went down, just like we expected. Flash Attention 2 did a bit better, but it still had some variation in those metrics as the sequence length increased. But the Linear MoE models, they were the real stars of the show. Their memory usage stayed pretty much constant across those different sequence lengths, and the throughput remained consistently high.
So they really delivered on that promise of linear scaling with sequence length.
They did. And when they compared the inference efficiency, they found that a basic linear attention implementation was actually faster than Flash Attention 2 when you're decoding those really long sequences, those ones over 16K tokens. And even better, the memory usage for linear MoE during inference, it stayed nice and flat.
So no more memory explosions when you're trying to use the model to actually do something useful.
Exactly. And then they did these ablation studies where they looked at how much those MoE optimization techniques like group GMM and megablocks actually helped. And guess what? Those optimizations made a huge difference. They significantly reduced the training time per iteration.
So they're not just relying on the core algorithms, they're also really fine-tuning the implementation to get the best possible performance.
Right. And they also did some really cool analysis on the effects of using those different parallelism strategies we talked about earlier. They showed how you can really optimize your training process by choosing the right combination of those techniques.
Okay, so they've shown that Linear MoE is really efficient for both training and inference. But the ultimate test is how well it actually performs on real language tasks. What did they find there?
So they trained both their smaller A0.3 B2B models and those larger A1B7B models in two different configurations. They had a pure linear MoE setup where all the layers were linear MoE layers. And then they had a hybrid configuration where about 25% of the layers were those standard transformer MoE layers, kind of sprinkled in at specific intervals.
So they're testing out both the pure approach and the hybrid approach.
Exactly. And when they looked at the training loss curves for those A.3B B2B models, it was pretty clear that the pure linear MoE models were able to achieve a level of performance that was comparable to that standard attention baseline. And interestingly, those hybrid models, they seem to have even more stable convergence during training.
So it's like the hybrid approach is maybe a bit more robust.
Yeah, it could be. And the paper actually has a lot more detailed results in the appendix, including all the benchmark evaluations and the training loss curves for the bigger A1B7B models, if you're interested in digging into that.
Oh, I'll definitely be checking that out. But in a nutshell, how did Linear MoE perform on those standard benchmarks?
Okay, so overall, both the smaller and the larger Linear MoE models, they achieved some really impressive results on those language understanding benchmarks. They were right up there with the best performing models, and in general, those hybrid models, they tended to do a bit better than the purely linear ones.
Which kind of supports their idea that combining those two approaches can give you the best of both worlds.
Yeah, it seems like that hybrid approach is a really promising direction.
Okay, so after all that research and experimentation, what are the big takeaways from this paper?
Well, I think the main takeaway is that Linear MoE represents a really significant step forward in terms of making these large language models more efficient and more scalable.
Especially for those tasks that involve really long sequences of data.
Exactly. By combining that linear complexity of LSM with the sparse activation of MoE, they're really addressing some of those fundamental limitations that have been holding these models back. And those modeling and training subsystems they developed, they're incredibly flexible and they support this huge range of LSM methods and all those fancy parallel training techniques, including that specialized SP they designed for long sequences. Plus, they've shown that these hybrid model architectures, they've got a ton of potential too.
It's really exciting to see all these different innovations coming together. But as with any research paper, there are always limitations and areas for future work. What did they highlight as some of the key areas where Linear MoE could be improved or expanded upon?
Well, they point out that because you're combining all these different LSM and MoE methods, it can get a bit tricky to find the perfect set of hyperparameters. It's like trying to tune a really complex instrument. They also mentioned that they need to do more research to see how well Linear MoE scales to those truly massive model sizes.